Thank you so much. Uh, thanks everyone, both online and on site. I want to welcome you to this seminar. And my name, as I said, is Shegun Oke from University of from Alabama, A&M University in the United States. So thank you for the privilege. Today's topic title will be our speaker today will be talking about on the hidden symmetry of the SIRD epidemic model. And in his talk, briefly, he'll be telling us about the investigation, the Lee symmetry underlying the SIRD model, revealing a deeper structure that allowed the construction of exact solution and reduction of complexity by applying Lee symmetry analysis. And he will also be telling us about identified transformation that simplify the model, uncovering previously and unnoticed invariants that have implication for both theoretical understanding and practical application in epidemic modeling. These results open avenue for more efficient numerical scheme and provide insight to the underlying mathematical framework model. So without wasting much of our time, we have Professor Maba Boniface Matadi. He's an associate professor of mathematical science at the University of Zululand and is an NRF C2 rated researcher. He holds a PhD and master's in applied mathematics from University of KwaZulu-Natal and an honor degree in pure mathematics from University of Kinshasa, DRC Congo. His research focuses on differential equation and Lie symmetry with application in medicine and finance. Professor Matadi's work also explored the theory of distribution, invariance, principal symmetry in mathematical modeling, and approximate transformation, group distributing to the advancement of mathematical modeling and its real application work. Currently, Professor Matadi is also the HOD of mathematical science in the University of Zululand. Join me as we welcome Professor Matadi. Over to you, Prof.
Thank you. Thank you so much, Dr. K. Thank you, Chair. And thank you, Program Director. I really appreciate the kind introduction. Thank you so much also for your time. As you say, you are from the University of Alabama in the United States. I believe by this time you should have been sleeping, but you sacrifice yourself to come and attend this session and attend the presentation. And I would like also to acknowledge the Center of Excellence for providing me this opportunity to present at this weekly seminar. I also want to thank the center because my university is one of the node leaders of the Center of Excellence. And our staff, both our staff and the students have been receiving some funds from the center. So we are very grateful on that. My presentation for today, as the chair highlighted, will be based on the hidden Lie symmetry of the SIRD epidemic model. This is actually the model I developed a long time ago, and I've already published the paper, and that model has been cited more than 20 times with different scholars. So it has about more than 20 citations. And the focus here, I tried to study more because I realized that during COVID, most of the scholars used the same model to apply it to the COVID scenario. And it was very powerful. And then after finding in my previous paper, I only used this symmetry. But I conducted further analysis. I found another symmetry that was hidden, and it helped me to find more solutions. That's what I would like to share with you. It's actually a four-dimensional nonlinear differential equations. As you know, differential equation is a useful tool where you can model any real-world scenario. As I mentioned, most of the scholars use it for COVID-19 situation. And then the nonlinear system can also help you to predict for prediction's sake. Yes, so as an agenda today, I will start by giving an overview of our model, just an overview and also an overview of a symmetry method because of the time. And then it will follow by giving some type of symmetry. And I will now talk about the hidden symmetry because this is the purpose of today. And then how I discover the hidden symmetry of our model, then I will conclude. Yes, the SIRD model that I developed, as I said, a long time ago, it's actually a compartmental model and which divides the total number of population into three categories, which are susceptible, the infected population, the recover, and the dead population. Now, the least symmetry analysis it can reveal some hidden symmetry that are not immediately apparent. As I say, in the previous one, I couldn't find it, but now I discovered that hidden symmetry. And then in this presentation, I will explore more on the hidden least symmetry in this model and the implication for understanding the spread of the infectious diseases. Yes, as you know, the nonlinear differential equations, there are so many techniques or methods that is available in order to analyze a nonlinear differential equation. So I just highlighted few of them. There are so many that are available, and each technique has its own advantages and also limitations. Now, for the purpose of this presentation, I'm going to focus on the least symmetry method, which is part of the analytical method. It can help you to find analytical solutions. And this technique was initially discovered by Sophus Lee. And in the same token, I would like to acknowledge my former supervisor, Professor Peter Leach, who recently reached his 80 years old. I think it was few weeks ago. He's the one who initiated me to this technique. He supervised my PhD and master's. Yeah. And I'm going just to highlight the advantage and the limitation for the technique of least symmetry. In the context of differential equation, when we say symmetry, what does it mean? It just refers to a transformation that leaves the differential equation invariant, the your nonlinear differential equation change, actually. And now the advantage of this technique, it actually gives you some tools, some transformation. It will generate the transformation in order for you to reduce the complexity. Because remember, we are dealing with a nonlinear differential equation, which is so complex. And then this technique will help you to reduce that complexity and also to reduce the size of your problem. It can also provide insight into the structure and the solution of the equation. But beside those advantages, it also has some limitation. That's why most of the scholars run away from this. Usually, if you find that the problem is difficult and then you need to publish as quick as possible, you run to a more reliable, like approximation technique. So the limitation is more on it requires the advanced mathematical tools and also to identify the correct transformation in order to reduce the complexity. As I say, it's sometimes so challenging. Now, this is the type of symmetry that we have. This is very useful because I'm going to use it when I will talk more on the hidden symmetry. So I'll let us to highlight what is a contact symmetry is basically a transformation that involves a symmetry that involves transformation that affects both a variable and their derivative. For instance, if you look at this first order PDE here, you can see that those transformations here involve both independent and dependent variable and also their derivative. Now for point symmetries, these are the transformations that involve only independent and dependent variable directly. Okay, so there is no derivative that is involved here. So if you look at, for instance, this first order ODE, the transformation here only involves both independent and dependent variables. And then for local symmetry, these are the transformation that depend only on the variable and their finite derivative. So you can even get more derivative from the transformation, the second derivative. It depends on the equation you are investigating. Now, if you look at this Laplace equation, you can see that this is the transformation that is involved there. And the non-local symmetries basically is the transformation that depend on the non-local expression. You can see if you look at this Verga's equation, we have some non-local expression there, this integration. It's a non-local expression. So this is a non-local symmetry. And now the Northern symmetry is more used to analyze some conservation law in physics. And then it's very important for those who are studying some physical model. Now, the hidden symmetry now, it has been observed that after reducing an ODE, by reduction of ODE, reducing an ODE, I mean that you're decreasing an order, and now reducing a PDE is you are decreasing the independent or dependent variable. Now, when you reduce a PDE, you reduce it, you can get an ODE, because the more you reduce your independent variable, you can get your ODE. In 1994. They are actually important because they reveal deeper insight into the structure and the behavior of mathematical and physical systems. It's also leading to simplification. As I said, that here we are dealing with a nonlinear system, which is much, much complex to analyze. And then we have type 1 and type 2 hidden symmetry. For type 1, these are the symmetry that are lost after reducing your differential equation. You will see that you have your initial equation you are analyzing. You investigated from Lie point of view, Lie symmetry point of view. You have certain number of symmetry or transformation. And now after conducting your, those symmetry will help you to reduce. And then when you reduce the order for the case of ODE, you find that some symmetry are lost. So these are type 1. And when you conduct the reduction, and then you find that you gain some symmetry. In my case, in this model, I gain some symmetry. So these are the type 2 hidden symmetry. Now, the origin, we actually want to know the origin. That's what Abraham and Guillaume did. So they would like to find, after discovering that there are some hidden symmetry, they would like to find out their origin. Okay, are they local, as we discussed in the previous slide? So in case of ODE, the hidden symmetry can arise from a contact, a non-local or a point symmetry. And for PDE, remember, for reducing a PDE to a ODE, that those symmetry, the origin will be a point symmetry. We define the point symmetry. And for reducing a PDE to another PDE, the origin can also be a point symmetry. I know there are so many researchers who are investigating more than, I'm not saying that it's only point symmetry, it can be non-local, it depends on the research you are doing. And now, let me just give you a few examples to understand then I will take you to the model. So considering this 4-order differential equation, analyzing this equation from Lie point of view, we got those 3 symmetries that is there from equation 2 to equation 4. Now the idea here is, after finding those symmetries, which one is reliable to reduce your equation 1? Because the idea is, this is so complex to solve. And now we need to use the technique of Lie to reduce the order in order to make it more simple for you to get a analytical solution. And now we've got those 3 symmetry, and then we would like to find out which one is can be used to help us to find those transformations in order to reduce the order of equation 1. Then we conduct the Lie bracket, that's what we call for Lie bracket. And by Lie bracket, we found that G1 can be used. So we use G1, the phase symmetry, in order to reduce. And from G1, we got those transformation here, the transformation, U and V, that allow us to reduce this equation 1. So we basically reduce it to order 3, which was from order 4 to order 3. So which is much good, but it's still challenging. Equation 5 is still much challenging to solve. Then we conduct again, we analyze it again from the Lie point of view, and then we found these 3 symmetry. And now we realize that the first 2 symmetry here, X2 and X3, are inherited from the previous one. But the X4 is now our hidden symmetry. It's our hidden symmetry. And now we would like to find out the origin, as I say, for Abraham and Guillaume, they study the origin of the hidden symmetry. And now we study the origin of this X4. That's what we did, the next line. And then we realized that the origin of X4 is a non-local symmetry. As we can see, as I say in the previous slide, we have the non-local term here. So the origin of our X4 is a non-local. Okay? But X4 was the the more reliable one to reduce, because remember you got X2, X3, and X4 from G1, G2, G3, you're still having some challenge to solve your equation, because equation one, you come from equation one, which is four order, then you reduce it to another equation to a third order, which is still a nonlinear. Then you start again, you conduct more investigation, you find X2, X3, and X4, and then we realize that X4 is more, it's our hidden symmetry, because X2 and X3 inherit from the previous study, previous analysis. Now from the X4, which is a hidden symmetry, we come out with those transformation here, with W, our new dependent variable, and T, the new independent variable. And now it reduced that equation 5 to equation 10. So you could see that equation 10 is more easily to solve. Okay. And now we conduct again the equation 10, Lie symmetry, equation 10, and then we found those 8 symmetries. Remember, for a second order symmetry, usually have 8 symmetries. And now from those symmetries, we realize that W3 and W5 inherit from the previous analysis. And now the remaining, because if you remove 2 here, W3 and W5, which inherited from the previous study, the remaining 6 are hidden symmetries. And then here, I just conclude that X4 was the correct symmetry to reduce further equation 5. Now, the second example here I'd like to give you is, the first one was for ODE, now it's for PDE. It's a PDE now. This equation was studied by Abraham and Kesh Lavender in 2006. They actually found those 4 symmetries. They analyzed this equation from the point of view and then obtained those 4 symmetries. And now what happened is they actually combine V1 and V2. Why? Because the linear combination of the symmetry is also a symmetry. So they, after combining V1 and V2, they use now VA and then lead to those transformations. And this transformation here with Y independent, newly independent variable, and W new dependent variable, it reduced that complex PDE. Remember, we said that a PDE can be reduced to an ODE, or by doing a reduction, you can get another PDE. So in this case, you got a ODE, that's PDE is reduced to an ODE, and now conducts further Lie analysis. We come out with these seven symmetries, and now discover that X1, X4, and X6 inherited from the previous analysis. So remove 3, so the remaining 4 symmetries are type 2. Remember, we defined the type 2 hidden symmetry and type 1 hidden symmetry. Now, in summaries here, so we basically, when you are analyzing your original PDE, you analyze it just as we did, I explained before. When you analyze, you come with some symmetries. You analyze a nonlinear PDE from the point of view, you come out with some symmetries. And now you see that you still need some further investigation, because you still have some attempts to solve your equation despite finding those symmetries. And now, after conducting more investigation, you end up with a more simple equation, okay? And this equation has more symmetries than the original equation I used studies. So basically, the simple equation is your child PDE, which has more symmetries than the parent, than the original equation. And then conduct again more investigation from the Lee point of view. You will end up with a new parent. The new parent, by new parent, I mean that is your equation that's coming from the child that has the same characteristic with the original and the child, your child equation. Now, having said all these things, I would like now to apply those techniques into our nonlinear differential equation. This is the model I was talking about. So this four-dimensional nonlinear differential equation. So basically what I did, I reduced it into, it's a four-dimensional, I reduced it to a three-dimensional, because the idea here, when you study this system of nonlinear, first order nonlinear differential equation, you end up with a infinity number of symmetry. And if you have an infinity number, it's difficult for you to find the correct, the appropriate transformation. So that's what I did. So this is just explaining those parameters there. And so what I actually did here, I reduce it into a three-dimensional with one equation of the second order. So basically, I isolated the number of susceptible population. I put it in terms of number of infected, and then I differentiate, and then we substitute it into the infected, the number of infected population. Then we come with equation 27. Okay, and now we made some rearrangements. I know it requires a lot of calculation here. I don't want to give more details. Then we come out with equation 28. And now we realize that equation 28 is still more difficult to analyze, and then we conduct this change of variable, and now we come with more, that looks more simple equation 30. But it's still complicated, because you know when you are studying, you have so many parameters, it's difficult to analyze it from the Lee point of view. Then we call, and then we call mu1 and mu and minus mu1 A, and then gamma plus alpha plus mu2 minus mu2 is B to reach equation 30. Now we analyze equation 30 from the Lee point of view. We found out that we have those infinitesimal coefficients, which psi and eta, equation 33 and 34, which has actually four constants, arbitrary constants. That's tell us that we have actually three infinitesimal generator, which has x1, x2, and x3. Now, as we discussed before, which one is the best in order to reduce our equation 30? Then we conduct our Lie bracket, and now we realize that x2 can be used to find the transformation in order to reduce the order of that ODE. Yeah, so we use x2, which leads us to find this transformation. Okay. And now our equation 30, now it's reduced to 39. It's reduced to 39 with y, our new dependent variable, and x, new independent variable. And now we investigate equation 39 from the Lie point of view. We found those 8 symmetries. Now we realize that G1 and G2 and G4 inherit from the previous analysis. So basically the remaining 5 symmetries, hidden symmetries. So from G4 to G8 is hidden symmetry. So these are the hidden symmetry I found from the previous studies. Now I use G4. I basically use G4. As I say here, the remaining 5 symmetry I type 2 hidden symmetries. And now I use G4. G4 leads us to those transformation here, okay? And basically reduce our equation 39 to this first order ODE equation 42. And now here it's just a matter of going back, because when you find your solution, you must go back to the original variable. That's what I actually did here until I found, I remember the number of infected we assuming to be equal to U, this U over beta. So this is the number of infected population that is found. And we also doing also some substitution. We found the number of susceptible population. And now we use our third equation, okay? Remember, we reduced the equation into in the 4-dimensional, and it was reduced to a 2-dimensional. 1 second order that was lead us to find the number of infected and the number of susceptible. And the remaining 2 are the first order. The first one is 49, which lead us to find the number of recovered population, and then we find the number of dead population. Okay. And now here we just do some plotting. I plot those solutions to take the reliability of my solution. I found that it makes sense, because as the number of susceptible population is decreasing, I mean, for the number of infected population is increasing, the number of susceptible population is decreasing. And basically, obviously, the number of recovered and dead population is always less than the number of infected population there. In conclusion, so hidden symmetry offer powerful tools for analyzing and simplifying differential equations, including those modeling in epidemic. The SIRD model, when analyzed through the lens of symmetry, yield deeper insight into the dynamics of infectious diseases. Further research into hidden symmetry in epidemic model will enhance our understanding and control of disease outbreak. So this is some references I use, and then I'd like to thank you so much. Thank you. You are muted, Doc. Yeah.
Thank you so much. I think program coordinator, you want to say something, right?
Yes. So I've unmuted the chat, I've re-enabled the chat function rather, for those online, if they want to type in any questions and ask, because now should be the 15 minutes for the question and answer session. So just for anyone online, I've activated the chat function. If anyone wants to ask also a question, they can just raise their hand. If maybe typing is too big a deal, you can literally just raise your hand and you will move to the top of the queue and we will unmute you so that you can be able to answer your question. But thank you so much for the presentation. I will now open up any question. All right, so there's a question on site.
Okay.
Yes.
Yeah, so these symmetries, you say they were hidden symmetries.
Yes.
Do those not come out if you take the 4th order prolongation of the generator? Because usually the infinitesimals that are contained in the prolongation will contain the terms that you would have had in your first order prolongation. So do those other hidden symmetries not come out if you just prolong the generator?
I think it will. I think it will. It will come out. It will come out. Because usually, if using that prolongation, it requires a lot of calculation, isn't it?
Yes, yes, yeah, a lot.
So yeah, so usually I use a SIM package. I don't know whether you are aware of a SIM package, and which use Mathematica. And now I'm actually avoiding with those long calculation by hand.
Yes.
So I use a SIM package, and then from that SIM package, that's what I'm revealing those symmetries and helping me to solve my equation analytically. Yeah.
Okay, perfect.
Mm.
All right. I'm trying to see if there's any questions online.
Mm.
So, Prof, for the same packet that you, the one of Mathematica, is it open source, or one is to subscribe before you can use it?
I got it from my supervisor. There are also some open source that use Maple, but I never use it. So this one I got it from my supervisor. But I believe, and he gave me the contact of the guy, I forgot his name, Stereos. He's from Canada, and we are in contact. Many times, if I'm conducting from my analysis, and I've struggled, I've got some challenges, and I will send him an email, then he will advise what needs to be done. Yeah, I don't think, and it's also open. It's you can see it on Google Scholar. He published so many on Google Scholar. It's available. Yeah, it's available.
Thank you.
Mm.
So Prof, it looks like there aren't any questions online. The chat is fairly clear. So just a reminder to everyone that is joining online, the session is recorded. The recording will be available on our YouTube channel in the next week or two. So if ever you want to revise or go through something Prof said on the presentation, please do subscribe to our YouTube channel. So it's just CoE-MaSS. You just Google CoE-MaSS and we will pop up, and you will get all our other presentation videos on there also. But otherwise, I think it's safe to say we are done for the day. Once again, thank you so much, Prof, for the insightful presentation. I hope all the people that were joining and were listening in actually gained a lot from your talk.
Yeah, thank you. Thank you also to Dr. K again. Okay, again for your availing yourself, to chair the session. Thank you so much. I really appreciate it.
You're welcome, sir. Thank you, sir.
Okay.
So I will now stop the recording and end the. Enjoy the rest of your day, everyone.
Thank you.
Thank you. Bye, Prof.
Bye. Bye.